Hello everyone, my name is Frederik Hammers and I'm a group leader in drinking water microbiology at EWAC. This presentation will be about stagnation and flushing and how this influences Legionella concentrations in building plumbing systems. This work formed part of our research in the LeCo project, specifically work package 5 and 6 that dealt with building attributes and how that influenced Legionella concentrations. In order to understand the role of stagnation and flushing with respect to Legionella, it is important to understand the various factors that favor Legionella growth in building plumbing systems. The first of these is temperature. While Legionella can exist over a relatively broad range of different temperatures, they tend to grow optimally in a narrow range of approximately 35 to 42 degrees. As for most other bacteria, Legionella grow best in the absence of chemical disinfectants such as chlorine or monochloramine. They also seem to prefer materials that leach high concentrations of assimilable organic carbon as nutrients. Coupled to these, Legionella exists typically in the presence of biofilms, which contain a diversity of other bacteria, as well as protists, which serves as the host for Legionella to multiply in the environment. As will become evident from further slides, stagnation or low water usage systems are typically the type of environments where these conditions can occur. The point is, complex building plumbing systems contain a diverse amount of microenvironments which create potential niches for Legionella proliferation to occur. So what happens during stagnation? When the water stagnates in your pipes, the hot water is going to cool down while the cold water is going to warm up. In both cases, this will go towards temperatures which are more favorable for Legionella to grow. In case there are disinfectants present in the water, these disinfectants will be used up during stagnation, allowing concentrations to decrease, again becoming more favorable for microbial growth. Depending on the type of pipe material, organic carbon may leach from the pipes into the water and accumulate during stagnation. This organic carbon will serve as nutrients for the general microbial population, allowing for biofilms to grow. Of course, the absence of flow means also the absence of shear stress. This may result in biofilms which become more accessible and more relaxed, that may allow for protists to graze on these biofilms and for Legionella to proliferate in these growing protists. Of course, these first 4 points are all favorable for growth. It is also true that during long stagnation, it is inevitable that nutrient depletion and starvation will take place as the bacteria are using up the organic carbon and phosphorus in the system. This will lead to starvation of the population and eventual death of the microbes. One of the challenges in this specific field is that stagnation per se is not very well defined. For example, short-term stagnation would be stagnation that occurs over a period of hours. Think, for example, your shower hose or the final meters of your building plumbing distribution system during normal everyday use. These systems would be mostly stagnant but would be flushed every 12 to 24 hours. Moderate stagnation, on the other hand, would be for a couple of days. Think for 2 to 3 days, for example, such as in your private home when you go away for a long weekend. Long-term stagnation would be stagnation that occurs over a period of weeks to even months. Here, good examples would be schools during the summer break, holiday homes which are not used frequently, seasonal sporting facilities that open only some times of the year, and even as a very well-known example now would be pandemic shutdowns which lasted for weeks to even months in some cases. What is important is that the biological processes that govern these different periods of stagnation are most likely not the same, and hence it is absolutely important that stagnation is well defined in terms of the plumbing system and in terms of the stagnation period in order to understand what is truly happening. So one of the fundamental questions is whether stagnation really favors Legionella growth. Prior to the pandemic, this specific publication from 1984 was cited by many authors as the foundational literature claiming that Legionella grow during stagnation. What you see over here is the data for 4 water tanks, 2 of those stagnant, 2 of those continuously used over a long period of time, a little bit more than 1 year. On the y-axis you see the concentration of culturable Legionella pneumophila. Now what these authors have shown is that for 2 of these water tanks that were online, meaning they were flushed continuously, the Legionella concentrations decreased rapidly during the first month of use and then remained low throughout the period. So far, so good with respect to stagnation and Legionella growth. However, the data deserves a little bit more scrutiny. Highlighted in this figure, you see the 2 water tanks that were stagnant during the experimental period, and these show varying results. The first water tank, which you see at the bottom, started with very low numbers of Legionella, and these remained low for most of the stagnation period, only increasing maybe in the last couple of months a little bit. The other stagnant water tanks started with particularly high concentrations of Legionella pneumophila, which increased during the first 2 or 3 months of stagnation, but then decreased during the remaining period of stagnation until the concentrations were more or less as low as the water tanks that were continuously flushed. So although this is a really great data set, it is argumentative whether it teaches us much about whether stagnation favors Legionella growth in building plumbing systems, for 2 reasons. Firstly, the results were varying without any question, and secondly, this concerned large water tanks of approximately 7,000 liters each, which is not necessarily representative of building plumbing systems and the pipes in the last meters of such systems. More recent literature seems to confirm these variable findings. This interesting study on the left was a collaboration between a large group of co-authors during the pandemic, where they looked at 26 reduced occupancy buildings in 11 cities throughout the United States, Canada, and Switzerland. What these authors found was that building-specific factors and disinfectant type seemed to have been more significant with respect to Legionella presence than low water usage, which would also be defined as stagnation during the pandemic period. In fact, the pandemic was, of course, a magnificent catalyst for multiple drinking water stagnation studies worldwide, because there was a broad concern for possible secondary problems with respect to Legionella growth arising from all these stagnant buildings during the lockdown period. This has also led to the rapid development and release of flushing guidelines on a national and international level in order to mitigate potential risks arising from Legionella growth in such buildings. The study that I will discuss today was indeed one such pandemic-related case study. This was done right at the start of the LeCo project, and it was done on a large building which had 6 floors and more than 150 different taps. Importantly, this was a building with historical Legionella pneumophila contamination, which we were studying prior to the pandemic, which meant that we had also data for Legionella pneumophila available before the lockdown period started. So the goals of our study was to document the changes in Legionella following stagnation, as well as following the flushing and recommissioning of this building. We found some interesting results, and the second goal of the project was then to explain these results through follow-up experiments. This slide shows an overview of the timeline of the project. As you can see, the last data set before the pandemic were collected on 24th of February, literally a few days before lockdown started. The building was then subjected to 7 weeks of stagnation, where occupation was estimated around 5%. So importantly, we're looking here at low water usage rather than complete stagnation. We then collected 62 water samples at the end of the 7-week stagnation period, right before flushing was done. A day after collecting these samples, we flushed all taps in the building according to the local guidelines. We then collected water samples during the reoccupation period on a weekly basis, and it is estimated that building occupation was around 30% in this period, which means an increase but not optimal water usage in the building. So let's look at some data. This figure on the left shows you the Legionella pneumophila concentrations in the building as measured with Leisure Alert and shown on a log scale. And as you can see, even before the pandemic lockdown started, the Legionella concentrations at all taps were already particularly high. Now, the first astounding result from this study was that after 7 weeks of stagnation, Legionella concentrations did not increase, but in fact decrease by at least an order of a magnitude throughout the entire building. This was a bit surprising, but the stagnation was anyway followed up with an intense flushing event of all 150 taps in the building. A week after the flushing event, when the building was reoccupied again, the first Legionella concentrations surprisingly showed an increase in Legionella at all the different taps in the building, and this trend was continued for at least another week before Legionella concentrations started to decrease throughout the building over the reoccupation period. And so a couple of key questions arose from this study. The first is whether the stagnation period really was as problematic as one thinks, since the concentrations decrease. And the second point is that the small increase that was seen after flushing made us ask the question whether flushing actually created more of a problem than providing a solution. So this begs the question, how is it possible that remediation flushing made the problem worse? We worked from the hypothesis that some of the Legionella contamination in the building may actually come from the boiler itself. It is well known that the bottom part of hot water storage systems may have temperatures favorable for Legionella growth. Once extensive flushing reduced the thermal barrier in the boiler to a level where it was no longer sufficient to kill the Legionella, it is possible that the system became contaminated with Legionella from the boiler, which was then distributed throughout the entire system, and where the Legionella then proliferated in the weeks after the flushing event. To study this further, we followed this up with specific flushing experiments on the building itself. In order to test this hypothesis, we did an experiment where we flushed the building's boiler on a single day through a single tap. The figure on the left here shows the percentage of boiler flushed on the x-axis, where you can see we flushed the boiler twice its volume in one day. And on the y-axis, you see the concentration of Legionella pneumophila and Legionella species measured with Leisure Alert and PCR from this single tap. Now the data is pretty clear. As the boiler is flushed, Legionella concentrations at the tap increase throughout the day until a given point when these concentrations drop quite dramatically. How we explain this data is that Legionella is either dislodged from the plumbing system or more probably flushed directly from the boiler into the building's distribution system, and then at the point where the boiler volume is flushed nearly twice empty, cold water from the outside distribution system would be entering the building plumbing system, and this cold water is likely to contain very low, if indeed any, Legionella concentrations, and this is when you see the dramatic decrease in Legionella concentrations at the tap. The figure on the right shows you the follow-up data after such flushing experiments were done, again with the date on the x-axis and the concentration of Legionella pneumophila on the y-axis. And what you see over here is that directly following one of these flushing events, you see an increase in the concentration of Legionella pneumophila by nearly a log unit in the 3 to 4 weeks after the flushing event was done. This was repeated twice, so it is pretty clear that the act of flushing did not only contaminate the system on that specific day, but that this contamination persisted through several weeks after the flushing event. So what do we conclude from this? First, I want to make the very clear disclaimer that this is a single case study. As we've seen now from different studies, different buildings will have different results. However, what we observed in this specific study was that 7 weeks of stagnation did not result in Legionella growth. Rather, we observed an overall Legionella decrease in the system. The remediated flushing which we did in fact not lower Legionella concentrations, but rather resulted in an increase in Legionella concentrations in the building. We believe this increase was caused by contamination of the system from overflushing the building, so from Legionella that were flushed out of the boiler into the system and which then persisted throughout the building system. Now, these results do not say that stagnation does not cause Legionella growth. There are clear examples of this. It also does not say that one should not flush contaminated buildings. There are examples where this has worked very well. But it does show us that all of these findings may be more nuanced and should be considered on an individual building level in the future. Following the COVID-19 pandemic, a large number of studies dealing with stagnation, flushing, and Legionella growth have been published in peer-reviewed literature. I show here just a small example of some of these studies. However, the general conclusion from these studies is that stagnation was an important environmental factor for Legionella growth in buildings. However, the results from the different studies were also shown to be variable, and it indicates that there's a complex interplay between stagnation and other contributing factors when it comes to Legionella growth. This brings me to the end of my presentation. If this was interesting and you have any further questions or comments, feel free to contact me directly at the provided email address, or go to the question and answer section on the main page and leave your questions or comments there. This is also a reminder that there are several other interesting presentations in this series, and I warmly encourage you to go to those and enjoy them as well.